All right, so I actually recorded this video, but somehow I forgot to switch on the microphone. So I will just walk you through that very quickly here. So the solution is already shown over here, but it's pretty straightforward. So first of all, I will look at this diagram and I will denote this distance between the charge Q1 and the point P by R. This is the same distance as the charge between Q2 and the point R. So I will denote it just by R to simplify things. I need to find the magnitude of the net electric field at the location P. Okay, to find this, I will have to first find the electric field due to the charge number 1 and due to the charge number 2. So for this, I will place a test charge at this point P. Okay, test charge is positive always, and I will ask myself, will it repel or attract the charge number 1? Well, it will repel, so, and this is would be the direction of the electric field due to the charge number 1. Now, what about the direction of the electric field due to the charge number 2? Well, here's a test positive charge. Here's my charge number 2. And since they're opposite inside the charge, so opposite to each other, then they will attract. Okay, so, and here is the directions of the electric field E2. Fine. Now I will ask myself what I would like to find the magnitude of the electric field E1. So the magnitude of the electric field E1 is given by the Coulomb constant times the magnitude of the charge Q1. In this case, Q1 is positive, so magnitude or not, it doesn't really matter. And divided by the distance between the point P and the charge number 1. And this distance be denoted by R. It is given actually, as a matter of fact, over here. Okay, so we divide by distance R squared. So from this diagram, it's pretty clear that if I would write the electric field vector due to the charge number 1, it will have only non-zero x component. Okay, and the first thing I would like to always cross-check myself if it is positive or negative, and in this case, the directions of the electric field due to the charge number 1 coincides with the direction of the x-axis, right? And therefore it is positive. The y component of the electric field is 0 in this case. What about electric field due to the charge number 2? Again, the magnitude I wrote down over here. This is the Coulomb constant. We know its numerical value. This is R squared, it's given in our problem. And this is the absolute value of the charge number 2. Now I would like to write the components. Again, from the figure, it's pretty clear that the x component of the electric field due to the charge number 2 is 0. And the y component will be negative, right? So because it is opposite in direction to the y-axis. Okay, negative, and that's the value. Okay, so the net electric field is given by the sum E1 plus E2. It's a vectorial sum, right? And therefore, what I need to do, I need to add the x components together and then the y components together, and this will define me the required vector E1, E net. Okay, so what about the x component of the E1 vector? Well, it is k times q1 divided by r squared, written over here, plus, well, I add here 0, it's the x component of the vector E2. So for the vector, for the y components, we have for E1 0 over here, plus I add, I add the y component of the vector number 2, and comes with a negative sign over here, and I just rewrote the rest of it. And that is given by, well, we can just simplify and cancel all these zeros, remove this plus sign, and this will be our final result. Now we want to find the magnitude. This is what we eventually need to find, not just the vector, but the magnitude of this vector. So for any vector A with the components ax and ay, the magnitude is given by the square root of ax squared plus ay squared, as written over here. So, well, here we have a very specific vector, and we want to find its magnitude. So we will take the x component squared, written over here, we will take the y component square written over here. So the magnitude squared will give me just q2 squared, right? So, and this minus sign will disappear once I square it, it will become just a plus sign. Okay, and this I can a little bit simplify. I can pull out from the square root this k square into r square, r to the fourth, and when I do this, it will be just k over r squared square root of q1 plus q2, and this will be my final result written in this analytic form. Of course, at any stage of this process, you can actually substitute the numbers and work with just the numbers. I prefer to work with in this notation, okay, but it's up to you. So you can substitute the numbers. You need to remember that nanocoulomb is given by 10 to the negative 9 coulomb, and millimeter you need to also convert to meters. So 55 millimeter is given by 55 times 10 to the negative 3 meters. So once you do this conversion, substitute all the numbers, you obtain this result approximately. Okay, please cross check me. So this is 51,200 Newton divided by Coulomb.